Okay, I think that's on now, right?
Yeah, that's good.
Okay, great about that. So the theme today is anomaly detection as we continue to explore data analysis and particle physics. And I'm going to draw the same picture I've drawn a couple of times. So we have our goal is to understand nature. We do that by performing some experiment, for instance, colliding particles, and then getting out particles, making some measurements, reconstructing the particles, and then, yeah, sometimes observables at the end if we can't accommodate high dimensions. And on the theory side, we have some theory which is parameterized by some parameters, and we want to see if that's a good theory or not. So we have basically exactly the same path on that side. And in the first lecture, I talked about how we can do this inference task for parameter estimation by directly comparing RICO particles at the level of the end of the simulation chain or the experimental chain without having to first compress into observables. So that was lecture 1. And then yesterday, I talked about how we can go backwards in the simulation chain to do inference at the level of particles before they hit the detector. So that was lecture 2. And I ended yesterday by talking about how in all of this, we rely heavily on the simulation, both the particle level simulation, that was essential for the first lecture, and the detector level simulation, which was essential for the second lecture. And I ended by saying, wouldn't it be great if we could do inference tasks where we don't rely on the simulation at all? And that is going to be the setting for today. So why do we need something else? And my motivation is sort of threefold. So one is the obvious one, which is the conclusion from the last 2 lectures, which is that simulations are no good, are unreliable. And our simulations are excellent. And in many regions of phase space, it's impressive the accuracy and precision we can achieve. But they're not good everywhere. Of course, all of our simulations are an approximation to nature. And so there are some regions where they're just no good. Another motivation, which honestly is the one I'm most excited about and the one that keeps me up at night, is that we just don't know what to look for. What if the new physics has already been measured, we just don't know to look for it, and it's just hiding underneath a pile of other stuff that we've ignored? So that is a key motivation. Motivation is the case where your parameter space is huge. So imagine I do know what I'm looking for. I have a theory, but there are way too many parameters. And the problem with that is that usually we specify some model. We say, for instance, dedicate a search to look for that particular model. That could involve machine learning, training a classifier to distinguish simulations of the theory from, say, a background. But if I have a lot of parameters, it doesn't. So for instance, the minimalist SUSY incarnation, MSSM, has hundreds of parameters. And so in practice, when people do a SUSY search in the 100-dimensional space, instead, they project down into a 2-dimensional space. Usually it's a 1-dimensional space. This is the so-called simplified models, where you think of everything for stops. Their math is all that's relevant. I ignore everything else. So if I wanted to imagine a very large parametric space, then anomaly detection, even though I know what I'm looking for, still could be quite effective. OK, so the new tools that we need to address these challenges are anomaly detection. And in the last 2 lectures, I spent a lot of time, almost half the lecture, talking about the classical approach. And then I said, OK, the classical approach is no good, so we need to use machine learning to make it better. But in this lecture, there is no classical approach, basically. There's just the machine learning one. And so I'm going to get to the machine learning much faster in this lecture compared to previous lectures. OK, and the goal here is to develop tools that allow us to automatically look for new things without having to specify a lot ahead of time. And we need basically, we basically need 2 pieces. Uh-oh. I lost my, there we go. Okay, we need basically two pieces. As for any search for new particles, we need to be able to be sensitive to signal. And we need to be able to estimate the background. If you were in the public lecture on Monday, one of the things I talked about was point anomalies versus group anomalies. So a point anomaly is one where you look at a single example and you know it's weird, whereas a group anomaly is one you only know it's weird in the context of other events around it. And we're basically never in a situation where we're looking for point anomalies. You can't tell from a single collision, for instance, if it's something weird. And so we're always in the example, with a case where we're looking for group anomalies where we have to be able to estimate the background. Things are only weird because we know what the standard model background looks like underneath it. And the way I like to think about different approaches is in the continuum of model dependence. So the more physics model dependence you input in, the more sensitive you'll be to the models in that class. And the less physics structure you impose, the more broadly sensitive you'll be, but the less sensitive you'll be to anything in particular. Okay, so that's the trade-off. And so in kind of the way I think about it, there's sort of both for the signal sensitivity and for the background estimation, you can be sensitive to the physics model you decide you choose to target. So I'll make these two. So signal dependence So the way I think about it, let's say on the left-hand side here, for the signal sensitivity, to achieve signal sensitivity, I'm going to pick an approach. And up here, you have approaches that depend a lot on the signal you're looking for and on the way you're going to estimate the background. And over here, you have no assumptions, basically. And so we'd like to have approaches that are not in the top right corner. That's the goal here. And so in this top corner, the traditional searches, that would be like you specify a signal, a very particular signal, and you devise a strategy to look for that particular signal. So for instance, you train a classifier to distinguish signal from background. So that's like, I don't know, 99.9% of all searches live up in like top corner. Then there's a series of other approaches, which is what I want to talk about today. And I'm going to give them machine learning names in a little bit. But for now, let me just give them colloquial names. So in this bottom corner, the way to be insensitive to the signal that you're trying to look for would be to look for things that are not background. So if I say, look for things that are not background, then I'm not specifying what the signal is. I'm just saying it's not background. OK, so that's sort of like down here. Then there are sort of the off-axis ones, which would be like, let's start up here, it's easier. Up here would be, imagine I have a simulation of the background, and I train a classifier, for instance, or devise a strategy to distinguish the data from background. If I know the background really well, I'm very dependent on the background, because I've, like, say, simulated it, or I have a model of it. But if I just use the data directly, I don't care. I'm not specifying a signal model. The other corner is down here. This would be like, for a particular signal, let's say I specify a particular signal, and I want to develop a strategy to distinguish it from a background-enriched data sample. So this corner is not really anomaly detection, because I'm specifying the signal. But it's a very common strategy. For instance, let's say you're looking for like the Higgs. You know exactly what the Higgs looks like. But a lot of the background processes for Higgs, say Higgs to gamma gamma, are not very well modeled. And so we might want to use data as a stand-in for background and develop a strategy that way. But I'm not going to talk at all basically about over there. We want to be signal model independent as possible. So I'm mostly going to talk about these strategies today. OK. And I'm going to focus almost entirely on the signal sensitivity. But I will say a few things about the background estimation, because it's really important. It's what distinguishes this anomaly detection for us from other areas. Yeah?
When you say not background, doesn't that depend on what your background is?
Yeah, so not background is sort of like a, you could say like inconsistent with yeah. I'm going to talk about this a little bit more later, but you're right. It's sort of like, it depends how you estimate the background, whether it's here or over there. Yeah. OK. So let me just say a few things about estimating the background. So the most signal model independent thing you could do is to simply use simulation. So if I simulate the background, then I don't have to make any assumption on what the signal looks like to estimate the background. And up here is great because I don't have to assume that the signal is resonant. I don't have to assume anything about it, basically. But I'm very much dependent on how I model the standard model background. I have to be able to simulate all the sub-processes and yada, yada, yada. So that's up there. Down here, an example would be like the bump hunt. So if I assume that the signal is resonant, then I can do a parametric fit to the background. I imagine it's a steeply falling distribution, and I don't have to assume anything then about the background, other than that it's featureless, which it basically always is in the standard model. But I have a very strong assumption the signal is localized somewhere. Okay, so that's like the opposite end of the spectrum. No simulation here, but I have to assume that the signal has a particular structure. And there are things in between, so I'll just write some names. I won't explain them too much. So kind of in between, the one step away from using simulations directly is to use simulations with a small correction. So experimentalists would call this like the control region method, where you have a particular region that you want to estimate the background of, and you have a region next to it where you're pretty sure there's no signal, and you can kind of use that to play off each other to calibrate the standard model, the signal, the simulation. And then matrix methods are kind of even one more removed from that, but I don't want to spend too much time talking about it. Basically, the idea of matrix methods is that you have two directions. Both are signal sensitive, and they're kind of independent from each other and in the data, and you can play those off each other in order to estimate the background totally in data, but you have to assume something about the decorrelation of these two dimensions. Yeah. And machine learning could actually play a role in all of this, but like I said, I'm not going to talk much about it. I'm going to focus in this lecture almost entirely on the signal sensitivity. OK. And I've totally lost my, this is totally no good. My page disappeared. I don't know where it went. Uh-oh. This is no good. OK, well, I'm going to have to ad-lib then, because the next page I don't have, but that's OK. OK, so like I said, I'm going to focus on the signal sensitivity. I'm just going to reproduce that picture. And now I'm going to give them different names. Down here, or up here in the top corner, this would be what the machine learning people would call supervised. So supervised in the sense that I'm going to train a machine learning model where for every example, I know what is signal and what is background. So if I simulate a signal and I simulate the background and I train a classifier to distinguish them, I can tell the classifier every event, signal versus background. So that's up there. Down here, what I'm thinking about is unsupervised. And unsupervised, there are no labels. So I have a machine learning where I don't tell it what's signal and what's background. And then in the corners, I'm going to call this semi-supervised. In the sense that I have partial labels. So for instance, in the bottom right, I have labels for signal, but not for background. In the top left, I have labels for background, but not signal. So those are what I mean by semi-supervised. And then in the middle, there's a whole set of weakly supervised strategies where I have some labels, but the labels could be noisy. So I tell the model signal versus background, but they're not exactly correct. OK. And so I'm going to focus basically entirely on the not supervised approaches. And I'm going to talk about unsupervised and weakly / semi-supervised for the rest of the lecture. OK. That's really a bummer. I totally... just totally disappeared. Technology. OK. So generally speaking, the idea of the unsupervised strategies is to look for things that are rare. So we want to posit that if there is something new in our data, it's going to be rare. And by rare, I mean has a low likelihood of occurring. So let me talk about unsupervised. OK. So here we mean, yeah, usually we're looking for things that are rare. And so by that, I mean, we want so if we're looking for things that are rare, which means they have low likelihood, we need to be able to estimate the likelihood. And there's sort of two ways of doing that. You could do it explicitly. So explicit would be like estimate P directly, P a background. And then you'd say look for events that have low probability under the background. And then implicit, this would be estimate the some proxy for that. So estimate a proxy for the likelihood. And so in this class, the kind of exemplars that I'll spend a little bit more time talking about would be normalizing flows and autoencoders. So I will now describe those in a little bit more detail. OK, I think you got introduced to normalizing flows and autoencoders a little bit in the first week, but it's been a week and you've covered a lot of stuff since then, and I have different notation, so I will spend a little bit of time describing those. So let's start with normalizing flows. OK, so normalizing flow is a particular neural network architecture that allows us to directly estimate probability densities. And what's special about probability densities is that they integrate to 1. So a generic neural network does not integrate to 1, but normalizing flow is a type of network that integrates to 1. So that's what's their magic. And the way they work is based on the change of variables formula. So this is the change of variables formula between one random variable z, another random variable x. Because I have a map, f, that goes from z to x, and then f inverse goes from x to z. And so f is invertible. And I can compute this Jacobian determinant. So if I can do that, if z has a nice distribution, like a Gaussian, so I can compute this first term. And if I can compute the Jacobian determinant, then I can get the density of x. And the idea is if you chain a bunch of these together, then you can have pretty complicated f's as long as your original distribution has a nice distribution. So as long as the original distribution z is nice, like a Gaussian, and you have a bunch of f's that can be nonlinear, then you can model complicated distributions for x. And these are trained using the log likelihood. So the loss is because I have the explicit likelihood, I can just compute the log likelihood of the data and find likelihood that maximizes the likelihood or minimizes the minus log likelihood. And then, because I have a direct estimate of likelihood, the anomaly detection is to look for small values of the likelihood. And here, I should note that the probability density of the data has dimensions. X is dimensionful, P of X is also dimensionful. And so I can't say like P of X much, much less than 1, because that's kind of nonsense. And so in practice, what happens is that you sort of order all the events based on P, and you can take like, I don't know, the 1% weirdest ones. So that's the normalizing flow strategy.
You still probably need the simulation of the standard model background, right, to know what to expect. So you're not really cutting out.
Great. Yeah. So the question was, how do I train this? Do I have to use a standard model prediction to train this model? And in fact, so you could do that. You could train it on a standard model background, and then indeed you depend on the simulation, although pretty mildly, because if you make some mistakes, the mistakes here are not so egregious. On the other hand, you could also train directly on data. And various studies have shown that you can train directly on the data you're trying to look at, and if there's a little bit of signal, it doesn't contribute much to the loss. And so this allows you to cut out most of the normal stuff, even if you're training directly on the data set you're trying to test.
But the assumption then is that you're looking for a qualitatively different event than would be in the background. Like if it's just an excess of an event that like happens in the QCD background anyway, then you probably have a much harder time finding it, right?
Absolutely. So these tools, this one and the autoencoder I'm going to talk about in a second, have mostly been used, say, in industry to look for point anomalies, things that have basically zero probability of happening. And so I'll talk about this in a little bit more in a little bit, but that's you highlighted a challenge of these unsupervised approaches is that they're not targeting anything in particular. They're just saying look for something different. And so if something is like very common but overdense, then it won't find it. That's right, yeah. Mm-hmm.
Is there a reason to use like normalizing flows in particular as opposed to like a diffusion model or something like this?
Yeah, so the question is why a normalizing flow and not another model like a diffusion model? So the advantage of normalizing flows is that you get access to the likelihood directly, P, whereas a diffusion model you don't. So in diffusion models, often you have access to the score, which is the gradient of the likelihood, which is not super useful here. You could integrate it and get the likelihood, but it's not the thing we really want. Yeah.
Not so direct. Okay.
Yeah, exactly. But anything that gives you the probability density, it would be useful here. Only normalizing flows are basically that's like the main game in town for this approach. Yeah. Okay, so you could also look. So that's for the direct density estimation. Then there's the indirect one. And the example there is autoencoders. And for an autoencoder, the loss looks like this. A vanilla autoencoder, where let's say the data are in some space, and I call it G maps Rm with m less than n, and then f goes back. So the idea is that you have two functions, an encoder and a decoder. The encoder takes my data and maps it to a space that's smaller, and then you have a decoder maps a smaller space to a bigger space again. And so an algorithm. So the idea is if you want to be able to compress with G, uncompress with F, and you train it so that the compressed and uncompressed looks like the original. And the point is that if your compression algorithm is doing its job, it should allocate its capacity. It should be very good at compressing and uncompressing things that are very common. And it should be bad at compressing and uncompressing things that don't happen very often, if it's never seen them in the training data set. And so the kind of most widely used anomaly score, then, would be to look for cases where basically you don't reconstruct very well. So if you compress and uncompress, and that's very far away from the original, then you can say probably likelihood, and I look for those poorly reconstructed events. And so here I haven't estimated likelihood directly. It's that's what I mean by indirect. Okay. Yeah.
What does the subtraction mean here? Should I literally imagine just subtracting particle momenta in a list or something, or do people do or something?
Yeah. So you can do anything for that minus sign. So the question is, what does the minus sign mean? Because let's say x is like a vector or some complicated list of particles. Yeah. So it could literally mean think of them as Euclidean vectors and subtract them. But that may not be the best, and so you can imagine any number of schemes to compare two sets of things. Yeah, and in fact, there's all sorts of variations on the theme. You could also have a variational autoencoder or all sorts of other bells and whistles. But they all, at the core, this is kind of the idea. Okay. Okay. That is basically all I'm going to say. But before I move on, I want to talk about challenges with unsupervised methods. Okay, challenge. So the first challenge is that, which was also kind of mentioned, I think, hinted at earlier, is that rare depends on the coordinates. And so I think hopefully you can already see that from the change of variable formula here. So the point is that if I change my coordinates from x to x prime, then I pick up the Jacobian factor. And so the Jacobian factor, if it's a constant, then it doesn't matter. So for linear transformations of coordinates, rare is the same. If you pick the 1% rarest stuff, it's still the 1% rarest stuff. But if this Jacobian factor is nonlinear, then it can change the order of rarity. And so something that's rare before may no longer be rare. And so just to illustrate this explicitly, let me give you the most pathological example. So here's an example. Let's say I have some coordinates x, and I want to transform the coordinates into y. I'm going to So let's say I have this particular variable transformation. It's called the cumulative distribution function, but it doesn't really matter what it's called. I just make this integral transformation. And then the question is, what is the distribution of y? So p of y, I can just follow the change of variables formula. So this is equal to p of x, f inverse of y, df inverse dy. And so if you follow this through, I'm going to assume everything is nice, which it is. So I can just take the derivative of f with respect to x, and basically the way I've constructed f is that I basically just plug in p. So that's just p of x. So if you haven't seen this before, the distribution of the cumulative distribution function of a random variable is uniform. So you see this is just it's just one, a constant. And so basically, whatever the distribution of x is, say it's Gaussian or whatever, the distribution of y is uniform. So nothing is rare for y. Y, everything is equally likely. And so this is pathological in the sense that whatever you had was rare before, after this transformation, it's no longer rare. So this is one of the challenges of unsupervised learning, is that you pick different coordinates, the definition of rare changes. Okay. Yeah, challenge 2, which was mentioned earlier. Oh, yeah. For the autoencoder, what do you mean you don't need to change your coordinates?
Like we can avoid this problem if we use autoencoders instead of normalizing flows. Is it true or?
Sort of, not exactly, because if you change the coordinates, I mean, this is implicitly learning the density, basically. So if it's learning the density, it doesn't matter if it's implicit or explicit. If you change the coordinates, it's going to change what's rare. But indeed, actually here, if you have a nonlinear function, you can think of it like, if it's a linear function, it's just like a constant out front. Obviously, it doesn't matter. But if it's a nonlinear function, the notion of being close now changes, right? And so actually, yes, it will also change like the performance. It's more complicated because it's not exactly the likelihood, but implicitly it's estimating the likelihood or something like it. Yeah.
Maybe I just missed it, but on this side, are you starting with z and finding the distribution for the variable x, and then what is the relationship between f of x and z?
Yes. So the idea is that let's say z has a very nice distribution, like a Gaussian, which I can write down exactly. And x is the one I don't know, and I want to estimate it. And so I want to go from z to x. And so the normalizing flow would be a map from z to x. And then that allows me to write down the likelihood of x, the p of x. So p of x is what I'm trying to estimate.
And what's the relationship between z and f of x? Like, what is the f?
Oh, yeah. So f is a map from z to x. So my normalizing flow is a function that maps z to x. Yeah. And it has to be invertible so I can do that, which is actually non-trivial because most neural networks are not invertible. So normalizing flows have a lot of structure. You have to have an invertible function, and you have to be able to compute the Jacobian determinant, which is also non-trivial. Yeah. OK. And the second drawback, which I'm not going to have any explicit example for, is that I'm just going to write the word optimality. I'll just say, so challenge 2, I'll just say optimality question mark. So there's basically no limit in which unsupervised methods are optimal for anything. And so if they're effective, then it just happens to be that the signal you're looking for is rare using that definition, which it could be, but doesn't have to be. And so that is a general challenge with these unsupervised methods. I can't tell you one method is better than another method unless you tell me a signal to look for. If you give me a signal, I can tell you which method is better than another method, but then you've given me a signal, and I'm no longer signal agnostic. So I'd say that's kind of an open question, is how to think about unsupervised methods and how to compare different unsupervised methods. OK. So now I will use this board, I guess. So I'll spend the rest of the time talking about an alternative to unsupervised methods. Which is weakly supervised or semi-supervised. And so there are lots of techniques in this area, but the one powerful strategy I want to basically spend the rest of the time talking about is where you have data and you compare it against a reference. And the kind of setting is that suppose that the probability density of the reference is basically the probability density of the background. And if the probability density of the data is some mixture, then if I train a classifier to distinguish the data from the reference, then it's going to learn the likelihood ratio of P of data over P of reference. We spent the last 2 days talking about likelihood ratios. And the point is that the likelihood ratio of P data over P of the reference is monotonically related to the likelihood ratio of signal versus background. And so basically, P of data over P of reference is monotonic to P of signal over P of background. So that is a very powerful setting because I don't have to specify the signal. If I have a reference, which is the background, then training a classifier to distinguish the data from the background will basically automatically, anything different between the data and the reference will be a signal. So the name of the game here is basically how do I get the reference? And I'm going to spend most of the time talking about that. Now what I like about this setting as opposed to the unsupervised setting is that there's a limit in which this is optimal. So if it actually learns the likelihood ratio of data versus the reference, then it's monotonic with signal versus background. That's the best you can possibly do for any particular signal. And so that's a really nice setting to be in. Mm-hmm.
The classifier works event by event. I would think that doesn't make sense because a given event, it's not like it's either signal or it only makes sense to talk about like statistically in bulk. Single events.
Yeah, so the question is this classifier event by event? Because as I was ranting on earlier, basically it only makes sense to talk about statistically. Yes, so there are many ways you could use the classifier. So for instance, you could make a cut on the classifier and count, or you can just look at the performance of the classifier. If the classifier has any non-trivial performance, which is that's a statistical question, right? So event by event, you can't tell. But imagine like the classifier learns something non-trivial. So if you, for instance, look at like the area under the curve, and it's not 0.5, then you'd say, oh, it's learned something non-trivial. There must be a difference between the two classes. Or make a histogram of like the classifier score between the reference and the data. And those histograms look different. I'll give an example later how you would use this, but yeah, exactly. Event by event, you can't tell anything.
I have a question.
Yes?
Why would P signal over P background ever be monotonic?
Monotonic. By monotonic, I simply mean that if you take the ratio of this to this, which maybe I should just do explicitly. So this is equal to, it's going to be mu PS over PV plus 1 minus mu, something like that. And so the point is that this is monotonic. There's two functions, that function and this function. And this function is just in fact, it's not even monotonic. It's just a linear function of that one. So if that's high, this is high. And they're just a scaling. Okay.
I was wondering about does it just say PD over PR monotonic, not also PS over PB?
PS over, sorry, yeah, I want PD over PR to be monotonic with this. So just call this a new variable, and I want this to be monotonic with that. Yeah, as a function. Okay, so in practice, let me just say a little bit about how this optimality kind of shakes out. It looks a bit like this. So let's call this like, so let's say I want to measure the I pick a signal. So for a given signal, I want to know how good is this at distinguishing signal from background. And in general, it will look kind of like this. So this dashed line is the fully supervised. So let's say I train a classifier to distinguish signal from background with labels. That dashed line is the best you can possibly do. Up is better here. And for the weakly supervised case, if you have a lot of signal, it basically converges to the fully supervised case. If you have a lot of signal, it's almost as if you have labels, because P data is basically the signal, and P reference is basically the background. But if you have very little signal, and as the signal goes to 0, basically P reference and P data are the same. And so it's very hard to find the small amount of signal. And so this is what I mean by kind of the asymptotically, this approach is optimal.
Can you ever have a negative mu, like an underdensity or something weird?
So yeah, you can't. The question is, can you have can mu be negative? And there are cases where you have interference between the signal and the background. And in that case, it's not a mixture model. It's something more complicated. But indeed, something like this would work in that case also. Yeah.
So should I literally think of mu as like a relative cross-section of signal and background in my data set?
Yes.
Okay.
So mu here will be small, because if it was large, you would have already seen it. So we're talking like mu of like 1% or 1 per mil or even smaller. And in fact, that's what makes this classification problem different than most classification problems. Because here, the two classes, the data and the reference, are almost identical. When mu goes to 0, they are statistically identical. And mu would be like a little bit, maybe like 1% or something. You're trying to find a tiny difference between the data and the reference. That's the name of the game.
Is this like practical performance, or is this like some like theoretical proof? Like, I'm just confused because it's monotonically related to the ideal classifier, so it seems like it should just be a horizontal line.
This is in practice, but if I was stronger mathematically, I would be able to derive this. This is a fundamental limit basically from the information contained in the data set. So if I'm training a classifier using a finite data set, then basically I'm not able to get the optimal classifier. And so asymptotically, this relationship is true. That's why it converges to that. But for any finite data set, and the limit mu goes to 0 should be clear. When mu goes to 0, there's no signal at all. And so it's going to be basically random, whether it's good or bad. And in fact, that's the key difference between the unsupervised and the weakly supervised. The unsupervised case, if I drew the unsupervised performance here, actually, I'll just do that. So unsupervised would be like, so the unsupervised performance does not depend on how much signal there is, because it doesn't use the signal at all in the training. And so it's very, it's like when there's no signal, it has some non-trivial performance, but it does not converge to the optimal performance when there's a lot of signal. Okay. So then the name of the game is how do you estimate the reference? Yes.
So it seems that, yeah, it's very low value of U and supervised learning is better than the supervised one. So since when you start an analysis, you don't really know what's the fraction of signal versus background, like how do you, do you just do trial and error to know which one is probably better in that case?
So the question is, because we don't know how much signal there is, how do we know what method to choose? And in general, I would say I have two answers to that. One is that we need to use many methods. I think no one method is going to be the best everywhere. So it's great to have complementary approaches. But if you have some target types of signal models you're looking for, you can ask questions about which would be the best. So for instance, down here at mu equals 0, this has some non-zero performance. But that performance may not be actually useful in practice. So for instance, if you have zero signal, it doesn't that your autoencoder has some non-trivial performance, you still won't find it. And so there's a question about is this performance actually good enough to find it? And that's a question you could ask. Yeah. For a given signal. In general, I can't tell you. Yeah. OK, so how to get R? OK, so option 1 is use simulation. So here, then you're 100% reliant on the simulation. But as I said before, the benefit is you have no assumption on what the signal looks like. So I don't assume it's resonant. I don't assume whatever. It can be anything. This is a very generic strategy. Basically, train a classifier to distinguish data from simulation. The main problem is that this will just find all the problems with your simulation. So if your simulation is bad, this will be the classifier will just say, your simulation's bad, basically. And so here, you need your simulation quality to be at least as good as your signal is big. So if your signal is smaller than the deficiencies, you'll just never find the signal. OK. Option 2 is you could use, for instance, symmetry. To get the reference. So here's one example. Let's say you wanted to look at let's say you wanted to say look at mu plus E minus events versus E minus mu plus events. So in the standard model, they're the same. They should have exactly the same properties. But there could be some BSM. So for instance, I'll draw a diagram. So for instance, this is a leptoquark, a scalar leptoquark. And this scalar leptoquark, it has a preference for mu minus E plus as opposed to the other way around. And so you could imagine using all the features in the data, taking these two data sets, mu plus E minus mu plus, train a classifier, and if there's a difference, that might give you a sense that there might be something like this in the data. So the benefit here is that there's 100% from data, no simulation, so it's kind of the opposite of simulation. The downside is that, of course, it restricts what you're looking for. So you're only looking for things that violate the symmetry, which most things don't. This is not exactly a contrived BSM model, but it's not like the first one you'd write down, probably. And there are other challenges. So for instance, in the standard model, these two processes are about the same. But in practice, it's a little bit different because, for instance, the electron and the positron don't interact the same with matter because we're all matter and not antimatter. And so they're actually, the efficiency here is not the same. You have to apply some corrections to actually account for the fact that these are not exactly the same in practice. OK. The third option, and the one I'm going to spend the rest of my time talking about, is the case where you have a resonance. So if you have a resonance, that does require that I have some on-shell particles that are produced. But generally, you have some new heavy particles in your theory that are accessible at the energy of your collider, for instance, then you will have a resonance. And you can use sidebands. So the idea is that you have some mass dimension, and the signal will be localized somewhere. The background will be featureless. You can make a region around the signal, and then use a region away from the signal to estimate the background in the signal region. So you have SR is signal region, SB is sideband region. And there are many ways of estimating P of SR from P of SB. That's the goal here. And in general, I don't know where the signal is, usually, so I'm going to scan over this location. But I'm only scanning in one dimension, just this mass dimension. OK, I'll use this one. So there are many ways of doing this, and I'm just going to highlight a few. Yeah, and to be clear, the idea is that P of sideband, this is basically, there's only background in the sideband. So that's the whole point, is that the signal region might have some signal, but the sideband has no signal. OK. So one possibility, and this is, all of these methods have funny names. I will take credit for some of the funny names, but not all of them. So here, one option is to say, well, let's just estimate the distribution in the signal region as the same as the sideband. So if x is independent from m, this is great. So if x and m are independent, I just literally take the sideband data and call it my reference. So I could train a classifier to distinguish the data in the signal region from the data in the sideband region. And this works. This is great. I don't have to do anything special, but it very strongly relies on x and m being independent. If they're not, basically this will just tell me, oh, your features are dependent on the mass, for instance. But that's like the first thing you would try. Everything else basically tries to correct for the fact that the sideband and the signal region are not exactly the same. OK, so another option, and this is called cathode, is to approximate you could approximate the conditional density of x given m in the sideband using a normalizing flow. So imagine I used a normalizing flow, or this could actually be a diffusion model, doesn't really matter. I use some generative model in the sideband to estimate p of x given m, and it's conditional on m. So then in the signal region, I can sample x's from the data in the signal region, and I can train my classifier. So that's one option. Another option, which is called SALAD, is to do something similar, but instead of directly estimating the likelihood, you estimate likelihood ratios. What do I call it? P of data. Sorry. So say I have either a simulation or another data set of some kind, some reference. I could estimate the likelihood ratio of the data to that reference, say a simulation, in the sideband using a likelihood ratio estimator, like a classifier, and then I could interpolate that. And so here this would look like it depends on the simulation, but it doesn't matter too much what the reference is. The idea is I'm learning to correct the reference to match the data sideband, and then I can interpolate it into the signal region. For instance, like a classifier. So this is like the generative approach. This is like the discriminative approach to do basically the same thing. I'll give one more example. Called theta. And the idea here is that if you approximate kind of similar starting point, imagine I approximate p of x given m and p of for data and simulation using normalizing flows. So basically, I have for this one, I have so let's say f here is normalizing flow. It maps some Gaussian data z to the data in my either in data or in simulation. Then I can do something like in the signal region, I can map x goes to what it would be like f data f inverse sim. So I could take my data in the my simulated data in the signal region, map it to the Gaussian, and then map it back, to the data in the data space, and then this is like basically a way of correcting the simulated data, so it's just like SALAD, but instead of reweighting, it morphs it. So it's moving instead of reweighting, and there are advantages, pros and cons of moving versus reweighting, but this just illustrate that kind of goes beyond this kind of reweighting paradigm. And this is the dumbest way of doing this, and you should ask Rada for better ways of doing it. There are many more, including variations on some of these. So these are just like a few ideas. So here, basically directly use the sideband. Here, estimate a conditional generative model, like conditional likelihood ratio, conditional morphing function. And then, yeah, there are many more. So yeah, plus more, including variations. Okay, yeah.
For this to work, do you have to like play some tricks to get the region of the z's for fsim corresponding to like x to be similar to like I just don't see a priori any reason why like the z of fsim would be related to the z of f data.
Yeah, and the reason they're the same is because the base distribution is the same. So say I'm mapping a standard Gaussian to my data. So both normalizing flows are mapping to a standard Gaussian. So once you map to a standard Gaussian, it's a standard Gaussian. And then you can map back to anything else to get whatever your favorite distribution is.
So I guess, is that mapping like unique? Like would you expect like regions of the simulation to then map onto similar regions of the data?
Yes, so in one dimension, for instance, this would be accomplishing basically like the CDF transform. And there's no unique mapping between two distributions, but here the function, this f function is invertible, but it's not the only one. So this is ideally one nice feature about doing this is like imagine the data and the sim are exactly the same. Then this composition should be the identity. But there are other ways of getting that. So for instance, there are a bunch of symmetries in the data. So you could imagine if I map x to minus x, and then I map it back, it doesn't do the same thing. So there is definitely no unique way of mapping a data set to a Gaussian. Because you can always map it to, for instance, if you map to a Gaussian and you compose with them, x goes to minus x, it's still a Gaussian. And that would look like a big move as opposed to a small move. Yeah, so that's it. Yeah, that's why this is not the smartest way of doing it. There are other better ways of doing it that try to actually minimize the distance traveled. This composes two functions that don't know anything about each other. Yeah.
I apologize if it's a naive question.
I'm sure it's not.
Does it, I don't know, is it close to matching filtering that you have like the simulation, you pass it through the data, the noisy data, and then you have a spike in SNR, or it's totally different?
At some level, it's similar in the sense that I think you can think of the whole classifier itself as basically the filter. Because when you do a match filter, you have like a template, and you have to way of asking, is the template the same as the data as you scan it through? And so the analog here would be like, this is like the generation of the template, and then the comparison is the classifier, and the scanning through is changing the signal region. But otherwise, yeah, it's basically that. Yeah. Okay. Actually, let me be in the middle here. So I'm almost out of time. I'm running towards the end. And as with the previous two lectures, I'm going to conclude by declaring success. I'm an upbeat kind of person, I think. And so I've demonstrated here some tools that we can use to do anomaly detection. I talked about unsupervised methods, and I spent most of the time talking about these weakly supervised methods that allow us to compare data and a reference, and I talked about how you get the reference. And they're pretty generic. And we're actually starting to see first results, experimental results from these techniques. But it's just the beginning, and in part because there are a number of things left to do. So I'm going to spend a few minutes talking about that. So the good news is that we have a new toolkit to look for new physics, but there's lots of work left to do, and I would argue it's pheno work left to do. There's of course a lot of practical things left to do as well. There's some challenges that I think many of you will possibly be able to address. Okay, so let me talk about them. So the first question, which was asked earlier, is how do you use the classifier? So once I have the reference, I train a classifier to distinguish data from the reference, and then what do I do with it? So one option, as I mentioned, is you could make a cut. So take the most signal-like events, or the most data-like events according to the classifier, and then compare somehow the data and the reference, which might involve some other estimation of the background. So oftentimes, the reference is not quite good enough to be directly used to estimate the background, which is why you might need to use another method like a bump hunt, or one of the other methods I talked about at the beginning of the lecture. So in practice, what people do is they estimate the background twice. They estimate the background once to get the reference and make the classifier, and then a second time to estimate the background after making a cut. And usually the second one is simpler. So the reference here has to be the high-dimensional background estimate, but usually the second one is just a count. So you're just doing like a bump hunt or something in one dimension. And so the other question is, let's say I'm going to make a cut on the classifier. What cut do I make? I don't know how much signal there is, so I don't know a priori what cut to make. And in general, this is actually a problem. And what practical people do is they make a few cuts. They say, OK, I keep the top 1% or the top 1 per mil or something. But those are kind of arbitrary choices. And because I don't know what signal I'm looking for, I don't know what cut to make ahead of time. Another question is, let's say I train my classifier to distinguish data from the reference and make a cut. Can I look at the same data I used to train the classifier with? because I'm actually training a classifier on the data, right? Should I divide the data in half? Do I have to divide it in half? Do I have to do k-folding? These are all interesting questions related to like the look elsewhere effect. If I train and test on the same data, will I artificially make bumps or anomalies? And it kind of depends how you do the setup. But that's an interesting question. Challenge number 2, which is related to that. So for a standard, oh yeah, go ahead.
Since the classifiers give you the likelihood ratio directly, why not just use that instead of cutting on it?
Yeah, so the question was, if you have an estimate of the likelihood ratio directly, why don't you see lecture 1 and do inference based on likelihood ratio? And you could do that. Let's say I had an estimate of the background. Let's say I thought P reference here was actually quite good. Then that is exactly what you should do, because I have the optimal test statistic. In practice, the reference is usually not good enough, and the signal is so small that most events have a likelihood ratio which is very bad. And so if you just do the lecture 1 in that framework, you're going to have a lot of noise. So you kind of want to at least cut out most of the background. I mean, because your signal is so tiny, you want to cut out like most of the background and then try to estimate it. The analog would be, imagine most of your data points are not sensitive to the parameter I care about. Then you want to get rid of those so that you don't just basically just eat the noise. OK, so for most searches that are done, the way they work is an event selection is fixed at the beginning, and then you look in the data, do you see something weird? But the event selection is fixed so that, and that can be made public, so that all of you can pick your favorite model that's not the one the experimentalists use, and then check what would be the acceptance of your new model using that event selection. So you simulate a new signal model, and you check how many events pass the event selection of the experimentalist, and then you can compare with the reported data to get an estimate of the sensitivity. The problem here is that the event selection is not fixed. It uses the data. So basically, the event selection is train a classifier to distinguish the data from a reference. The reference is fixed. However, the data are not fixed. So if you have a new signal, and you were to have injected that signal into the data would change. And so if you had trained a classifier, it would be a different classifier. And as I drew here, the more signal you have, the better the classifier will be. And so in practice, these techniques are very hard to recast because you basically need the data in order to recast it. And so this is, in general, an open question. And it also makes it really hard to know what you would have found. So in a usual search, you have a particular signal you're looking for, and you can say what I didn't find. You set limits. But setting limits here is really hard. So imagine you do the whole procedure, you find nothing. What didn't you find? Because you're sensitive to a lot. And so the volume of models that you're sensitive to is hard to write down. And so in practice, what people do is they pick a few representative models that kind of probe the different directions in the parameter space, and they inject that signal into the data and just keep injecting more and more and more until you see it. And basically say, like, that's the limit I would have seen. And that is somewhat satisfying, but it's kind of only a taste for the sensitivity of these approaches. Number 3. While in principle, these approaches can accommodate any feature spaces, like X can be high dimensional, they don't scale very well when X is high dimensional. Because the more dimensions you have, the more fluctuations your classifier could pick up as being different between the data and the reference. And so being able to do really high dimensional anomaly detection is really hard. And in general, the way it seems like to do this properly is to impose some structure on the neural network. Don't let it learn anything. And then that allows you to kind of regularize a little bit. And there have been a number of papers in that direction. The last thing I'm going to mention as a challenge is that everything I've said so far assumes that I have the new physics already saved. But unfortunately, at the LHC in basically every experiment, a small fraction of the actual data that was generated was saved. These are called triggers. And so if you don't save the new stuff to begin with, you're never going to find it offline. And so it would be interesting to think about how could you modify these approaches to work online. And the difference between online and offline is that offline, you can look at as many events as you want, as many times as you want. But online, the problem is that you're in like a YOLO situation, which is that you only get to look once. Basically, every event, you look at it once, and you say, I keep it or not. Otherwise, you toss it. And that's a problem because we're talking about group anomalies. I already talked a long time about how no single event is anomalous. So if no single event is anomalous, how can I tell if I should save the event or not? And so basically, all these weakly supervised approaches don't work online because they're density estimator based, right? They're talking about densities. And online, I only see one event at a time. Now, for an autoencoder, you could train an autoencoder offline and then apply it and save the ones that have the worst reconstruction loss, for instance. But then what would you do with that? And I don't really know. Yeah. So that's basically, these are, I would say, the biggest questions, and there are some other questions as well. All right. So now you've heard my 3 lectures. I've covered a lot of topics. I talked about parameter estimation, I talked about unfolding, and I talked about anomaly detection. And I just have a few end remarks before I'm done. So first is that I hope I've illustrated to you some of the exciting tools that allow us to ask questions we simply couldn't ask before. So we can do parameter estimation in 1,000 dimensions. We can make 1,000-dimensional differential cross-section measurements. We can look for new signals we couldn't even imagine to look for before. So that is pretty exciting. And this is all within like the last 5 years. So it's like really the field is exploding. The other thing I'll say is that a lot of this innovation is being driven by physicists, and in particular by phenomenologists. Many of them are in this room. And so it's really an exciting area where it's not just machine learning people solving problems or experimentalists implementing tools from industry. It's really an area where physicists are developing new tools using physics, basically, to solve unique challenges that we face. And the last thing I'll say is that there are many things I didn't cover. I tried to give you kind of an overview from the statistical analysis side of sort of 3 strategies analysis, but in doing so, I left out a lot of things. And so I'll just mention a few topics. So I didn't talk at all basically about architectures. And there are a lot of interesting physical connections with architecture. So like covariant architectures, or what machine learning people would call equivariant architectures. Architectures more generally that take into account physical properties, like we talked yesterday about inference linear safety. And the list goes on. There are many, many other things that are related to each of these pieces, and then also unrelated, that are both on the experimental side and on the theory side in order to basically do the best we can possibly do. And the thing I will give you is the way I think about this is that my research direction is to think about physics problems in the lens. Cast my physics problem as a machine learning problem, and then we can do the best you can possibly do for a given task. And so if we can use that, then in principle, we won't leave any science on the table. All right, that's it.
Great, thank you. So you have time for more questions?
Mm-hmm.
Hybrid that you can do with the scaling, where say you learn a latent space using an encoder and then try to learn the density on that to basically reduce the dimensionality and use the same kind of tools that you're using.
Yeah, definitely. So the question was, can we approach the scaling problem by taking the high-dimensional space and projecting it, and then doing the density estimation there? And there the question is, how do you do the compression in a way that preserves the new physics? And so there have been a few papers on that. I would say with kind of mixed success. So you could imagine trying to say, I know my data preserve certain symmetries, like they should be Lorentz invariant and yada yada. And so then I could use that to sort of reduce the dimensionality of the data and then run your favorite method offline. And that works to some extent. And yeah, that is definitely one strategy. But all these strategies are about imposing some structure. So you could first compress imposing structure, or you could have the models themselves be structured so that they can't be like an arbitrary neural network. And those all seem to be very effective at scaling.
A sort of broader question. I was wondering if you can use any of these methods, for example, the unsupervised learning, to learn something about the quality or shortcomings of the fixed order predictions or like the simulations that you were mentioning. Can you like detect that there's something wrong in some base space region or something like that? Or how can you improve that?
Yeah, absolutely. So the question was, can you use anomaly detection not just for new physics, but also for, I guess I would call it like quality assurance or quality control? And absolutely. And On the experimental side, people are doing this already to look for like, I mean, there's like, if you have some detector with lots of channels and you don't want to look at them all by eye, you can use anomaly detection. I haven't heard of anyone using that for simulation checking, but maybe as a tool for automated diagnostics every time you change your Monte Carlo. I'm looking at, Stefan in the background because he's a Monte Carlo author. So maybe this is a way of automatically,
You're looking at something that's like unusual, rare,
Yes.
like
Yes.
that could be a problem with yeah, you know.
Yeah, definitely. No, I think that absolutely would be a useful tool for that. Yeah.
Are most of these methods like they can only tell you that there is a signal, not like where it is?
So the question is, I've talked exclusively about finding the signal, but not at all about what the signal is. And so I would be super happy if we found a signal. Then I would worry about what it is. But it's a very good question because sometimes knowing what the anomaly is helps you get confidence that what you found is real. And so the kind of inference part of the anomaly detection, I would say, is pretty wide open. Now. Yes. And so in that case, because it was a bump on kind of a known variable, you could estimate the mass kind of by doing a fit to the mass. But if it was more complicated, I would say that wouldn't work. And in practice, what people do right now is like you can like make your cut in your classifier and then like just visually inspect like what kind of events did it pick, and that maybe give you some sense of like what kinds of things. So there's a bunch of papers where people say like I just make a scatter plot of some various features of the selected events, and I can tell a story. But it's kind of unsatisfying. I would say this is a really interesting question. There are some methods where the method does return to you some information about the new physics, but it requires imposing a lot of structure on the problem. In a generic way, I would say it's wide open.
So suppose that I don't totally trust the experimentalists reconstruct the particles. I worry about pilot contamination. So is there anything that I could do about that?
Yeah, so the nice thing about the anomaly detection here, are you talking about anomaly detection or other just generally?
Just in general.
Yeah, in general. Yeah, so I mean, machine learning is playing a large role in, say, for instance, pilot mitigation and pilot, like this, all these steps, like all these arrows are basically people are also using machine learning to make them better. You can also use, various tools to help understand the mismodeling. Unknown mismodeling is definitely, nothing you can do about that, basically. And so it's important to design strategies that can, have flexibility to basically eat up things like that. Yeah.
Experimental data. Are there sort of available experimental data sets people can get their hands on to play with some of this stuff?
Yeah, so I would say first thing is that a lot of these tools can be developed using simulated data very effectively. I mean, there was a time, probably like Tazi 10 years ago, where the thing that a lot of model builders did was develop search strategies to look for new physics, for instance. And those strategies were developed using simulation. And I would say the new thing, now in present age, is that you should develop the same thing, but instead of developing event selections for particular signal models, developing new anomaly detection strategies. So that's kind of exactly the same kind of path. And there are a lot of data sets, like simulated data sets that exist. The LHC Olympics is one of them, where it's a public data set that now it's been open, so you can actually know what the signal is. But you can pretend you don't and see if you can find it. And there are actual data sets as well, but in general, the experimentalists are very protective of their data. And so I think for this audience, I think we're really in dire, I think we're basically still ideas limited. And so we need like new clever ideas for like solving all these critical challenges. So there's a lot of exciting research directions ahead, even just developing in simulation.